ನಂಬರ್ ಮೆಸೇಜ್ ಬಿಟ್ಟು ಹೆಚ್ಚಿನಾಡು చెప్పు చెప్పు
Sir, hello. So good afternoon. Because sir, hello. Sir, your voice is not audible.
Sir, good afternoon. Good
Good
afternoon.
afternoon, sir. Yes.
Sir, Girishji, what about the feedback in the morning session, sir?
Yeah, feedback is very good. Yes,
Yeah.
we received, sir. We will send it to you also.
Very glad. But some of our members got disappointed because they could not participate in Zoom meeting because of our limitations. So now that is 100. Yeah. So
100, yeah.
Yes, sir. So I hope that the response is very good and overwhelming. Yeah.
Okay, sir. Very nice, sir. Very nice.
Yes.
We are waiting for the speaker. Maybe in a couple of minutes he will join. Then we'll start, sir.
Yeah. Excellent, sir. Excellent. Some of the one of the member responded very well. I will forward it. So he enjoyed it, and regarding the Paul Rajgari, this thing first session.
Yes, sir. Yeah, Kannan Rajkumar sir joined, sir, today. Today's session speaker.
Okay.
I'll just give him a co-host option so that he can talk.
Okay.
Sir, good afternoon, sir. Kannan, sir. Yeah. Sir, please unmute yourself. Sir, we are able to see you, but
yes, sir. Sorry, sir. How are you, sir? Fine.
Yes, sir. Fine, sir. How are you, sir?
Fine. Thank you. Sorry, I thought it's 5 o'clock. Okay. Somehow
4 to 5.
4 to 5. I forgot actually.
Yeah.
So that it took a little time. Sorry.
Nice,
you were right. I was wrong,
okay,
actually. Thank you, Girish.
Thank you, sir. Thank you for joining. KNS Prakash Rao is a convener of that Industry Institution Interaction Forum, AP, sir.
Yes, sir. Good evening, sir.
Of the department also.
Good evening, sir. Good evening, sir. So thank you for accepting this session, sir. So
thank you, sir. I also thank you for inviting me for this today's lecture also.
All the members will be enriched with your talk. I'm sure, sir.
Who are the participants, sir? Participants will be engineers.
Academicians. Academicians are there, engineers will be there, and students as well also we are having.
Okay, good.
Some of the engineers, practicing engineers are also there, it seems, sir.
Okay.
Yes, they have joined. Yes, sir.
Okay, thank you, sir.
Yes, sir.
Yeah. So, sir, we reached 70. Shall we start? We'll go ahead slowly.
Yes,
so that,
yes, sir. Slowly they will come.
Yeah.
So what is the time, sir? Just 4 o'clock.
So, yes. Yeah, we'll start, sir. Okay.
Yes,
yeah.
Sir. We can go ahead.
Please go ahead. Yeah, Pujita, hello.
So meanwhile, I wish to Kannan Rajji. So regarding this forum, so Industry Institution Interaction Forum. So I will send the details to you later.
Okay.
But anyhow, it is a voluntary organization, voluntary body.
Yes, sir.
Composed of some senior members from both academia as well as industry.
Okay, sir.
We formed an organization, non-profit organization. It is only purely a service organization. The main objective is to bridge the gap between the industry and institutions, sir.
Good.
So by conducting such activities and by inviting eminent persons like you, and so that our main motto is to enrich the students and so as to bend their mind to practical approach. So that is the main motto.
Yes, okay.
So that by the time they enter into the profession, their job, they should not feel it is totally a different one. So they should have some sort of visualization, practical visualization. So that is the main objective, sir.
Okay, sir.
So I hope we will expect the same cooperation in future as well for this forum, sir.
Sure, sir.
Yes, sir. Thank you.
Right, sir. We are ready, sir. We will go ahead. Okay.
Yeah,
Thank
okay,
you.
start, sir.
Pujita, go ahead.
Yes, sir. Now, I warmly welcome you all again to today's national program on the role of structural engineer in sustainable structures organized by Department of Civil Engineering, Sri Vishnu Engineering College for Women, Bhimavaram, in collaboration with Industry Institute Interaction Forum.
Now, let's have a keynote talk on seismic resistant design and case studies in cost-effective construction technologies. Dr. P. Kannam Rajkumar, who has obtained his PhD in concrete technology from SRM University in 2014, he has 15 years of experience in teaching. He conducted many programs like 10 one-day workshop and geomaterial and special concrete and one-day workshop on ground improvement techniques for infrastructure projects. Besides all this, he was awarded with Best Paper Award for Seismic Response Control of RC structure using viscoelastic dampers in International Conference on Sustainability Technologies in Building and Environment and studies on high-performance hybrid fiber reinforced concrete with copper slag as a fine aggregate in the International Conference on Sustainable Environment and Energy in 2017. He published many articles like Seismic Behavior of Transfer Grids in Multi-Story Building, Investigation on Strength Properties and Microstructural Properties of Pozzolanic Mortar Mixes. Hereby, I hand over the session to Dr. P. Kannan Rajkumar Garu to hand over the session.
Thank you, madam, for a wonderful presentation. I will thank the organizers, Dr. Panak Girish Kumar, Prakash Rasa, for giving me this opportunity to have interaction with the industrial participants, academicians, as well as with the students. I'm audible, sir?
Yeah,
Girish
it's
Kumar?
quite audible.
Yes, sir. Okay, sir. Now I share the presentation. The screen visible, sir?
It's good, sir.
Okay, sir.
PPT, sir.
Okay. So now, actually, my topic was initially provided as seismic resistant design and case studies in cost-effective technology. Topic is on seismic resistant design and case studies in cost.
Sir, you are not audible.
Someone has muted me actually. Now it's clear.
Now it's fine, sir. Now it's fine.
Okay. So it was the topic is on seismic resistant design and case studies in cost-effective construction technologies. So now I'm going to give a two topics which will be entirely different forum on the seismic other than cost-effective technologies. Normally here cost-effective technology, normally people think it's low cost. It is not low cost. It is a good technology where the cost will be more effective, okay, at a lower cost. So my presentation will be like this. So initially I thought of not adding any uncertainties. So first I started with the uncertainties in design, then we'll go for earthquake resistant design, then structural systems and procedure for seismic resistant design, and then a small area base estimation, and then at the end I'll go for cost-effective techniques in construction. So first uncertainties. So actually this photo shows that a car was parked along the backwaters. Due to some reason, the car has fell into the backwater. A crane has come to lift up the car. Now you can see the crane is lifting up the car. So now you know that due to this, you will have an axial load combined with a moment. Okay, P as well as a moment, B into eccentricity. And what happens next? You can see the car lifted to the higher side. Then the entire crane has fallen into the system. So here the design engineer was able to, the crane fellow who was operating the system, he knew that the load carrying capacity will be more, but actually what happens is the load was accompanied by a moment. So this is uncertainty in design. So now what happens? Next slide. Again, you can see a larger crane has come. Say the load carrying capacity, I say it made 20 tons crane. Again, now it is lifting the car. So here also P will be same, the moment will be same, but the boom has been designed in such a way that you can take a larger load. Now this was successful. Next, again now they are lifting a very higher load. Earlier it was a very small car, or you can say small hatchback car. Now it is again a larger wheel load. A lorry, it is being lifted up. And now you can see that crane has been fallen back into the river with the same maximum load. Now from this we can know that the second crane should have come to lift up the car, and then a crane with larger capacity needs to lift up the crane. That is the basic idea. But basically we think that this is enough in carrying the load carry system. A similar thing we'll try to orient along with the civil engineering field also. This slide I got it from a Singapore professor regarding the loading criteria. Now next, we start with uncertainties. What is meant by uncertainty? Some unexpected load, or there may be some unexpected errors which may not be brought to the knowledge of the engineer. Either it may be civil engineering or it may be a structural engineer. Say for example, now as a structural engineer, I do myself own consultancy in college also. So we brought a drawing. Say for example, in the drawing it is going to be G plus 2 story. So I am designing the each story has been provided to me as such a 3.5 meter height each story. I design the columns such a way that each and everything with 3.5 meter. Suddenly in the site condition, the owner says that no, increase it to 1.2 meters so that I can place my truck or something, whatever it may be, to have a more car parking space, or that the client requirement may be increase the roof height so that I can come for I'll give you a very good rental scheme. Then suddenly what happened? Without the knowledge of the structural engineer, they will raise the height of the ground story. But actually the column designed only for a 3.5 meter height. But now what has happened? The column height will be 4.5 meter. Then instead of behaving the column, instead of behaving it as a short column, it may behave like a long column accompanied by a slenderness effect. It may lead to a failure. These are some of the cases in uncertainties where the people may not know they are making a mistake. So again here you can see you have a small balcony. There's n number of people are standing on top of the balcony. So the loading which the balcony has been designed, it would have been exceeded. Okay, normally as such a structural engineer, we should be very careful in designing a cantilever because it is subjected to catastrophic failure. Catastrophic means it is a sudden failure. Okay, so what happens here? The balcony would have been designed for live load of 2 kilonewtons per meter square plus the self weight. But you can see the people standing over there. 2 kilonewtons is approximately this 2000 kg per meter square. So you can see the load would have been gone up, but somehow the structure is sustaining. But the most of the failures in the balconies is due to the overloading. There are two examples my professor used to say. When you would have known about late Shivaji Ganesan, very famous Tamil actor, leading the cameo role in 1954 to 1980s and 90s and all. So due to sudden death, due to his possession of his death, most of the people used to come to the balcony and then they used to see the Shivaji Ganesan face in the death, in this possession. Then one or two structures was also failed because there's a huge load coming on either first floor balcony or second floor balcony where you have a very clear picture. So it was again a very good structure which has been designed for the actual live load, but the live load case has been increased due to the sudden increase in load. Second thing, my professor used to say that most of them used to occupy this external staircase in viewing the possession. So what happened? The external staircase also designed for 2 kilonewtons per meter square only, or maybe even 2.5 kilonewtons per meter square. You can see that sometimes 100 people or 150 people standing on the staircase, where again there will be uncertainty in loading. These are uncertainty in loading which will not be brought to the notice of the structural engineer. So design of balcony slabs. It is not as simple it looks to be. The span may be less, but it has some certain uncertainties. Because at the edge of the balcony, we provide a small wall. So later on, the next generation, they may have a small grill on top of the balcony wall. What is here that the lean wall. Again, they will be closing it to the top. So our next generation, they may consider a wall also the edge of the balcony without knowing the consequences, whether we can have an end wall at the edge of the balcony. So due to those reasons, we can see that there will be some cracks developed in the slab. And one more thing, when it is going to be a simply supported slab, either a one-way slab or a two-way slab, you may have a crack. That crack will get extended. Then what will happen? Again, it may get extended and the load is going to be high. Then the concrete is fall out. Then reinforcement will be exposed. Then the reinforcement will get corroded. Then only that will lead to a collapse. That is the case of a simply supported slab or continuous slab, whatever it may be. But in case of a balcony slab, you don't have this type of warning at all. It will be a sudden failure, or it may be a catastrophic failure, which may have a sudden collapse. Normally, these effects may happen in high-rise building, which was designed some 10 or 20 years back. So nowadays, we don't have any sunshades at all for our high-rise buildings because we go for a My1 technology wall. Entirely, it will be RCC wall. So those sunshades were sajjas, we call it sajjas. So what will happen normally? The reinforcement will be on top. For a balcony slab, the reinforcement will be on the top. But due to some reason or some constraints in the construction of 6 story, some story, what will happen? You would have pressed the reinforcement. Therefore, it will come down. Therefore, the concrete would have occupied the top surface of the balcony slab, which was not entitled to. Therefore, that may be a crack. Suddenly, it may lead to a failure. And all the people who are residing over there will think that since a small slab itself has failed, but what would happen to the entire building? It is not true. But normally, we may find some cracks and some failures in the cantilevers. And next, I'm going for a pattern loading. Many of you would have known who would do some bridge design. They would have come across the pattern loading. So pattern loading says in what pattern you are going to place the load. That is the criteria. So now example. So here I'm having a full UDL. Here I'm having a full UDL. So accompanied by dead load. Now I'm not discussing about dead load. The dead load will happen to any structure. So I'm having a full live load or 30 kilonewton per meter. Then what will happen? You will have two supports over here. So each support will take 120 kilonewton load. What will happen here? The maximum bending moment, exactly a center. It is 120 into 2 minus 30 into 4 into 4 by 2. That's it will be equal to 0. So what will happen now? If you're going to be young budding civil engineer or structural engineer, you'll think that bending moment is 0. Therefore, the maximum sagging moment is 0. You'll make sure that you provide only minimum reinforcement at the bottom without having a reinforcement because the bending moment is 0. Now, what will happen? A live load is going to place only at the center because live load is not practically we can't control the live load. Say, for example, I'm having a small marriage hall, or say it is going to be a longer span, and 2 ends I'm having a balcony. And 2 ends I'm having a balcony. Then what we assume normally? We assume that the total load will be taken care of in a STAT or E-taps or SAP, whatever it is. We provide total live load. Okay. Say the span is getting 4 meters. And then 2 sides we have a small overhanging on 2 meters. Suddenly, due to a marriage is going to take place, all people come to the center span. Am I right? All will come to center span. Then what will happen? Your load will be concentrated only at the center span. So, leaving there's no load at the edge. Therefore, your bending moment will be 60 kilonewton meter, even though your column loads are going to be less. So, in that case, there may be a uncertainty in loading by the structural engineer who you would assume that the loading has been taken care by the entire span of 8 meters. So if he's going to be a senior engineer, he will have some thought. He'll think that bending moment cannot be 0, and then he reanalyze and then he provide reinforcement accordingly. Whenever is going to be a new engineer is going to come out of the education institution, he may think that bending moment is 0. and then they provide minimum reinforcement as stipulated by the IS 456. So how to identify load patterns? So now we'll use the inflation diagram. So actually this type of loading we normally use to teach students, myself and along with the Professor Agustin sir. So how to introduce students the different types of loading condition. So for example, now whenever the ILD is going to go on top, it is going to be positive. Just give a simple example because many of you don't know what is ILD. Positive. When it is going to be down, it is going to be negative. Okay. So now you call it the hogging moment. Okay. So now load is going to be placed over here. Then you will have maximum positive moment. Load is going to be placed only at the overhanging. Then you will be having a maximum negative moment. So now pattern loading for beams. Say for example, I'm having a classroom, a continuous classrooms. Okay. So water measure span. So in the first ever class, all the students will be present in all the classrooms, normally in most of the colleges. And it's going to be third hour or fourth hour, one classroom will be left free because it would have been a free hours, whatever it may be. So all the students in this classroom would have gone to a tea break or lunch break, whatever it may be. Then what will happen? Here I'm assuming that I'm having a hinge over here. Okay. Therefore, what will be the pattern of loading? This will be the pattern of loading. Okay. So here I'll be having a positive moment, here negative, and here positive. Now what will happen? The total load multiplied by the positive, I'll get a maximum sagging moment. And here total load multiplied by positive, I'll get total sagging moment. If you place a load over here, the total load multiplied by negative, we'll be getting these two positive. Say this is going to be 1, and this is going to be 1, and this is going to be 0.5. And what will happen? 1 plus 1 plus 2 plus minus 0.5 will be 1.5 will be the total ILD. Since there is no load over here, then what will happen? The maximum sagging moment will be 2 when there is no continuous loading on the beams. When you come for second case, maximum hogging moment. So where will you get maximum hogging moment? So now I'm having a 2 loadings, and say these 2 classrooms are totally filled up over here. And third classroom is free, and I'm having a fourth classroom again filled up over here. Here I'll be having a negative moment, and negative moment. Then what will happen? I'll be having hogging moment. So here I'll be 1, say 1, and say this is 1. The total hogging moment will be 3. Therefore, a structural engineer should be able to place the loads appropriately in the software to get the maximum hogging moment in the second case. The third case, where you have maximum vertical reaction. I'm talking about the vertical reaction. For a vertical reaction, this is going to be the ILD pattern. Okay, it will be continuous. Okay, now add up all the loads over here, and that will be the reaction coming over here. When you place a load over here, then there will be a negative one accompanied. The maximum vertical reaction will be less. So when you go for STAD or any software, they do not cater this pattern loading automatically. It is the structural engineers or a civil engineer's point of view in providing the loadings to the systems. When live loads are of higher magnitude and fluctuate between these spans, then there may be a load position getting very critical. A pattern loading imposes more restriction and reinforcement because curtailment will be very important, because again, a positive moment, a negative moment, wherever there's going to be a tension, we provide the maximum reinforcement, and negative compression will be minimum reinforcement. And design has to be acutely aware of this so that the final design is safe under all conditions. Sometimes the reason is there will be a lot of reasons for unexplained structural crash can be attributed to the pattern loading. So this is a small example. So it's going to be a plinth beam. Okay. So on left hand side, I'm providing a brick wall. So the load may be 15 kN per meter. On right hand side, the load may be 15 kN per meter. In between, there will be iron grill. It will be less than 1 kN per meter. Then this is a practical example where we can have a pattern loading in a structure. So now next I'll go for earthquake resistant design. I switch off my video. So earthquake resistant design. So normally we know that all buildings are vertical cantilevers. I discussed about something about cantilever earlier slides. All buildings are vertical cantilevers projecting out from the earth's surface. Hence, when the earth shakes, these cantilevers experience a whiplash effect, something like a where you have maximum drift, especially when shaking is violent. Hence, a special care is required to protect them from this jerky movement. So buildings are intended to be earthquake resistant. Normally people think about most of the customers, they request that I need to have a earthquake proof building. Normally a civil engineer cannot design an earthquake proof building. He can design only a earthquake resistant building. So our intention is to design a earthquake resistant building. So building becomes more expensive if the design not to sustain any damage during a strong earthquake shaking. Okay, so normally we don't go for first case. Second case, they should be strong enough to not sustain any damage during weak earthquake shaking. Say, for example, in a local language, I say that Richter scale of 1 or 2. Okay, the loading will be very small. Therefore, it should not sustain any damage. Third one is they should be stiff enough to not swing too much. It should be so stiff also. You should be able to swing and come back to original portion. We call it as a elastic limit during weak earthquakes. And they should not collapse during the expected strong earthquake shaking to be sustained by them even with significant structural damage. Therefore, the building may not be intended for use, but it should not fail. These company demands are accommodated in buildings intended to be earthquake resistant by incorporating these 4 desirable characteristics as provided in them. So normally, if you want a building to be more earthquake resistant, the geometry should be good. Okay, the geometry shape, etc. building should be good. Say, for example, the geometry is going to be good, a square plan or a simple rectangular plan, simple rectangle, not a very long rectangle, a simple rectangular plan. Then what will happen? The moment of inertia will fall within the center of gravity will fall within the base. Okay, so you can say that the inertia forces are transferred to the base without any bending effect. Without any bending effect. So here you can see there's some odd shapes where the inertia forces will flow where you'll be having a bending effect. You can see a circular water tank or water, maybe you'll have bending effect. So these are the equilibrium forces where it will be accompanied by a small eccentricity, which in turn will create a moment setback into the structure. So seismic analysis procedure, there are 2 methods normally what we know. The one is equilostatic method. The other one is the response spectrum method. So the equilostatic method. So effect of earthquake are considered equivalent lateral forces. So everyone knows the formula. Base shear is equal to AH into W. So AH is nothing but a factor Z into I divided by 2R into SA by G depending upon the soil parameters. Z is the zone factor. I is the importance factor. I is the R is the response factor. And SA by G is the based upon soil parameter, you will be getting a graph. Into multiplied by the self weight of the structure. So everyone knows that Newton's law. Force is equal to mass into acceleration. Okay. So what is mass? Your W by G is nothing but your mass. Your W by G is nothing but your mass multiplied by the acceleration, SA. Acceleration due to gravity. Okay. So now, if you want to reduce the force, our ultimate aim is to reduce the force. Okay. You cannot reduce this acceleration due to gravity or earthquake force. We cannot play up earthquake forces. It is going to be a natural force. Only one thing what we can play is only with the mass. So now, therefore, if you want to reduce the force or base shear, our ultimate aim is to only to reduce the mass of the structure. How to reduce the mass of the structure? So you are seeing most of the temples in South India or across India. You see that the base will be very large. When you're going towards the top, the mass going on get reduced. The mass going on to get reduced. So here base will be very large enough. All temple gopurams. So here what will happen? The force at the base will be very less and going because of the reduced mass in the structure. This has been designed long time back by our ancestors in designing the temples. The same has been introduced in our structural engineering part as structural system. Okay, a schematic plan. So we call this a bundled tube. We normally call this as a bundled tube, or we call it tube in tube type of structure. So each and every tube will stop at different levels. Each and every tube will stop at different height. Therefore, the base shear calculated at the base will be very, very less. So a practical example is the Burj Khalifa. I don't know how many tubes are there. From the literatures I came to know these 20 tubes. Each tube will stop at different levels. You can see each tube is stopping at different levels. And at the end, there will be only a single tube projecting on top of the Khalifa, Burj Khalifa. Therefore, you can say that even though the 160 stories are more than 700 meters, the structure is going to be more safe because of the reduced lateral force due to the reduction in the mass. So the procedure for seismic resistant design. What are procedure? Let us most of you would have seen this. You would have seen the earthquake tips, okay, by C.V.R. Modi sir and Sudhir K. Jain, who have done a lot of work on this seismic resistant forces for the past 2 decades or 3 decades. So let us make the plan to be very simple. I just give a practical example also why the sample plan needs to be good. The first case and second case, the plan is a simple plan. Here, the corners are and curves. We call these re-entrant corners. We call these as re-entrant corners. So, the inertia forces flow to the ground level at a curve using a curvilinear shape. Therefore, there will be a torsion created in the corner of the structures. Similarly, for T-type structures. How to avoid these T-type of structures? You just separate these two structures. One is a smaller rectangle, other one is a going L shape. The vertical part, horizontal part can be separated. Therefore, there won't be any bounding effect or something like that. Therefore, the re-entrant corners will be avoided. Therefore, the inertia force flow will be different from the one part to the other part. So now you can see there are in part of elevation. The previous case was in form of plan, the form of elevation. You can see that the first case, the more loading is not so equal in all the columns. So this portion will be very high. Normally we don't not recommended by the structural engineers. And nowadays we don't design these buildings also because the promoters or the owners they need to have very large area. So this type of plans nowadays are ruled out. And again, these type of plans normally comes into picture before there was a collapse in 2002 Ahmedabad earthquake. So very long cantilevers on top, and you'll have weak flexible story. This is unavoidable nowadays. We have to go for a weaker flexible story, but make sure that you provide a shear wall, therefore reducing the shear forces coming onto the columns at the portico level. Similarly, unusually there may be a tall column at the ground level due to some other reason. You can make this column to be smaller by providing ties at different height. So we all know that the open ground story is like inverted pendulum. So as per the IS code, it says that the total seismic load should be multiplied by total seismic load coming on the column should be multiplied by 2.5. So instead of multiplying by 2.5, if you provide a small shear wall at the base of the system, then what will happen? The entire lateral forces will be taken care by the shear wall, and only a minimum forces will be taken care by the columns. Or minimum forces means it may be even nil force also, because the column will be designed only for gravity loading, whereas the shear wall will be designed for the lateral forces. So shear walls will take care of the lateral forces, and then gravity load will be taken care by the columns. Therefore, columns will be slender in section, needed to go for a very huge column for the open ground story. So these are some of the pictures due to soft story collapse. This was taken before 2002. You will see many pictures like this. So soft story need not be only the ground story. It can be even at higher levels also. Say suddenly they want to have a auditorium in the 6th story. Suddenly they want to have a very open hall in the 9th story. So the India has seen a lot of soft story collapse in the 2002 Ahmedabad earthquake. These are the apartment collapses, a soft story collapse. Many of you used to see that, see the collapse of building as only a loss to the owner or the customer or to the engineer who is going to build the building. But actually, when there is going to collapse more than 10 or 15 stories, there will be a economic curtailment in the country also. I'll give a small example what because at the time of Hakmada earthquake, I was 2002. I was a PG student in structural engineering in Madras University. So what happened during the Ahmedabad earthquake or Abuja earthquake, the prison wall has got collapsed. So what happened when the prison wall is going to collapse? Some of the inmates has been escaped out. Say some few hundreds have escaped out of the prison. So by the time they have barricaded the prison wall, because prison wall is going to be compound wall is going to be a very long cantilever. So normally during earthquake, most of the compound walls or staircases will be lead to collapse because it's going to be very slender section. You will not believe that within 1 hour, 99% of the inmates who have been escaped out of prison came back to the prison because they cannot survive outside because most of the structures are collapsed in the Bhuj and Ahmedabad area where they cannot have even livelihood take place in the system. That is called a worst socio-economic condition in India, which has been felt during an earthquake. Here you can see there's the open story. I don't know why they are provided as per the IIT Kanpur. So now to investigate the nature of soil to avoid soil liquefaction by proper geo investigation when it's going to be high-rise building, select good materials. Especially you can have a steel of 14% elongation and a yield strength more than 415 newtons per mm square. Nowadays, very difficult for us to get a yield strength of 415. So, whenever you go for a 500 newtons per mm square yield strength, make sure that the elongation is above 14%. Provide plinth beam at ground level, lintel, and roof band in case of masonry structure. So, this is actually we have gone for a competition in 2009 for IIT Rookie. The competition was conducted by University of Bristol from UK in coordination with the IIT Rookie. So they want to make students the feel of the earthquake. Mostly we say that we have a lateral force, a live load coming on structure. So they want to make sure that students want to have a feel of the earthquake. So that they gave a live competition. So where they will give you 20 crores of money as a dummy amount. So therefore we have to build a structure by purchasing each and everything from the store. Who is going to consider building at a lower cost and a maximum efficiency will be the winner. That is the outline of the competition. So this was our model. It was a 9-story building which was scaled down to 3 stories. So you can see there are small steel blocks over here. So these steel blocks acts as a live load, and below that you can see a A4 paper which acts as a slab. So each and every stick acts as a column. So we have provided bracing over here by using a thread. So everything was placed on a seismic shake table. Okay, now I'll show you some of the presentation video. One second, something has happened. I want to just end the session. Can you see the screen? Grisha?
Yes, sir. We are able to see the screen. Only video 1, video 2 is coming.
Okay.
Yeah. Yes.
This is actually a live seismic shake table where the load has been applied to all the 12 participants who are participating across the country. Actually, in the presentation, you would have seen that this, one second. You would have seen that this corner structure which was surveyed, but it was disqualified because they are used more than 16 columns. As per the condition, the column should be less than 16. So they have overruled the proposal and they have gone with 30 columns actually. You can see there were 30 columns with there. Therefore, they will be ruled out. Actually, they were the people which failure doesn't occur. So here you can see most of the structures, at the end, the jury has given the award to the third section over here from here. Somewhere. This was Atlas, this was the winner. You can see that most of the 12 stories over here, they are not provided plinth beam. They are not provided the plinth beam. We were the only people who provided plinth beam. So that was the reason for the survival of the shake table test. So most of them thought that providing a plinth beam, each and every stick costs nearly 4 lakh rupees as per the proposal. So they want to reduce the cost of construction. Therefore, they avoided the plinth beam, and then they provide lot of shear walls and all. Even though shear wall was able to resist the lateral load, but the most important is all the beams should be tied at the lower level to transfer the forces from the lower level to the upper level. So this small example I want to show you for the importance of a plinth beam. Again, structure system. Many of you would have seen that the Citigroup Center in USA is approximately 80-story building, but it stands only on 4 columns. Actually, this was the history of what I studied from the internet. So this was the plot size. Okay, this was the plot size. So they want to have at the corner of the plot, they had a small church. So they want to construct 80-story building. Normally, they ask the church people to sell the property to the customer, so that they will provide a church at different place in USA. So, but church people are so reluctant that they say that they don't know, we can't vacate the area. Then there are a lot of discussion going on, and then the church gave a different ruling. They say that you consider 80-story building, but don't disturb the church area, but instead you construct on top of the church. Understood, no? You can use my church area, don't disturb the existing church, but instead you can go above the church. Then this was the case what they have been provided. Your column stands on 4 columns. So the system for 10 stories, it was a single, only there will be only a core area. So they have gone for a cantilever on top. On top they are 80 stories. So this was the column positioning. They had only 4 columns. Center they had a core. So 4 massive columns. Columns of 4 are 4 massive columns. We call this as outrigger type of structure. We call this as outrigger structural system, where there are 4 massive columns. You will have very long cantilevers. Even though if you see the cantilever, so all are more stable because everything is balanced. It's again a balanced cantilever. So this was the shape of this system. Again, the difficulty what they faced was in the place is the core system. So core means now we know that we have a staircase core, we have a we have electrical outlet for a core, and then we need a lift core. Again, they had the number of lift they expected was 8 lift, the larger capacity, but they had a space only for 4 lift cars. So the first day they planned over here as a double-decker lift. Lift will be double-decker. So simultaneously the door will open at the ground level as it opened at the first floor level. I think so you can assume a double-decker bus. Okay, like that it has been developed. So you can see the height of structure. So here the beam depth will be more than 5 meter or 6 meter, where they have gone for transfer girder type of system. From transfer girder, they use the outrigger type of system, where beyond this the column size would have been reduced. Again, you see that the building rests only on 4 columns. There are different types of views you can get in internet. City Cop Center in USA. Next, I go base isolation. What is base isolation? To isolate the superstructure from the substructure. To isolate the superstructure from the substructure. Okay, when there is going to be a roller, we are going to place it below the superstructure. Then what will happen? Whenever there is going to be a ground shaking moment, the upper structure will not be able to, the inertia forces transfer to the superstructure will be very, very minimum. Okay, the hypothetical building on rollers. So now there are so many isolations coming up today. This was a very old isolator which was used in 2005 for a Buj hospital building. So at that time I heard from A.R. Santakumar sir, the total cost of each and every isolated pad was nearly more than 5 lakh rupees. So therefore the inertia forces going to the upper story will be 5 to 6 times smaller than a regular building. So this was a Buj hospital. This was a collapsed building during the earthquake. So this was the structure going on. So this was the lead rubber bearing coming on top. So this rubber bearing will be able to take care of the vertical load, the horizontal load, as well as the moment coming on the structure. So this is a lead rubber bearing pad which has been provided over here. Therefore, what will happen? This substructure will be able to take the maximum load, therefore providing a minimum disturbance to the superstructure. There are a lot of lead rubbers coming up today, where a vertical force, horizontal force, and nowadays they provide even active system, passive isolation system. Many are coming up. This is again the reinforcement has been protruded from bottom to top. So this was a small photograph I want to show to the participants. This I got it from Professor A.R. Santakumar sir. So where he physically has visited the earthquake during 2001 and 2 Buj earthquake, where this building is approximately 8-story, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10-story building. You can see the foundation size. It was hardly 1 meter by 1 meter. And then they have provided a pedestal, and you can see the column size. Okay, this is the foundation what they have provided for a 10-story building. So this was this building is surveyed for nearly 8 to 10 years. Then only it has collapsed. Then there are a lot of retrofitting. You can see there is a shear wall provided to the structure. But normally, whenever you provide a shear wall, the shear wall should be interconnected to the gravity system. Here you can see shear wall is very safe in resisting earthquake, but the surrounding structure has collapsed. Next is about the cost-effective technologies. I think I'm not running out of time. Cost-effective technologies. Why do you want to go for cost-effective technology? So because nowadays many people they invest more money on a structural system and or they're providing the masonry infills. So and then they use air conditioning to cool the structure. So they get the bricks from a long distance of say 30 kilometers, 20 kilometers. Then what happened to the diesel consumption? So the environment is getting depleted. So that whatever the material locally available, with the locally available material, we can construct the buildings. So actually this, I have worked along with Professor Sakti Rajendran from Tanjore, who has got a lot of structures, and he has shared me this PPT some 5-6 years back. And also I also worked on some 3 or 4 buildings on cost-effective technologies after having consultation with him. So why do you want to go for technology? Because everyone knows that the land is only 29%, the water is remaining 71%. Out of the water, only 1.6% potable water used for drinking. So for this drinking water, we use it for buildings, in construction, we use it for bricks. Then we get it from lime as a natural source, and cement where we deplete the carbon into the atmosphere, and then paint, granite, everything is natural material. We deplete it for use of construction industry. How to reduce these possibilities in the structure? So now, if the worth is say for example, this is what the example given by the Chuck Carter. If all the water can fit earth water, potable water, or the water can be filled in a gallon, only 1 teaspoon can be used for drinking. Okay, that's the example what I given over here. So when will these things compose? Whenever you say wood, it will compose for 1 year. When it's going to be wood stock is 1 year. Wood will take 15 years. Leather shoe 50 years. And plastic bag 1000 years to decompose. So therefore, we can reduce this material in the construction industry, or we can use this in the construction industry where we can reduce the depletion of the natural resources. So I'll take two technologies over here, cost effective. One is a rat trap bond, the other one is filler slab. Okay. So what is whenever we design a structure, a small, I'm not talking about a very high-rise building. I'm talking only about a 2-story building or a 3-story building. So we will be designing the outer walls as an English bond. Okay. So normally we know that these bricks are very good enough in as a thermal activator. Okay. So now what happened? There is going to be a high temperature outside. Only a small portion, a large portion will come inside the house. To avoid this, we use air conditioning. How to avoid this without using air conditioning? Okay, that is what as proposed by the Laurie Baker in Kerala. He has used a rat trap bond. Rat means Eli. In Tamil we say Eli. Rat trap bond, where a rat can be trapped. Okay, so this again 9 inches wall. This again a 9 inches wall. Okay, so where you will have 2 bricks placed like this. Okay, and then I'll be having a 3rd brick coming up over here. Again, I'll have a continuation of this course. Again, I'll be having a brick lining over here. Okay, this is total 9 inches. This is totally 9 inches. So this will be 3 inches. This will be 3 inches. Okay, in between you'll be having a 3 inches cavity. When it's going to be upper course, so I'll place a single brick over here. Then I'll be having a continuity of bricks over here. Okay, therefore, as we say that in English bond, the vertical joints will not be continuous. Okay, this is how we go for the system. So you can see over here. Okay, in between we'll be having a trap over here. So you can, as recommended by the engineers, when you use a filler rat trap bond, it is acceptable only for 1 + 1 2 stories. So instead, what we do nowadays is, when we go for G+3 building also, we provide columns. All the loads will go to the columns, and then these outer walls alone can be designed as a rat trap bond in order to reduce the increase the thermal comfort inside the structure. Okay, the major aim is to increase the thermal comfort. I show a small video how they place the rat trap bond. You can see the vertical alignment, each and every course is being disturbed. It is not a vertical alignment, will be not uniform. And in this case of rat trap bond, we go to use English bond. We use 1000 bricks. In case of rat trap bond, you will have a reduction in 220 bricks. But here the mortar, normally if we use English bond, is 1:7 mortar, am I right? Now here we have to use a 1:3 mortar to increase its strength because the contact area is very less. So what are the nowadays many people, they don't use brick masonry as structural material. But what are the advantages of using a brick made structural material is, whenever you have a lintel over here, the load is getting disturbed. Instead, we go for corbelled arch where the load flow will not be disturbed, or we go semicircular arch and again a Roman arch. So what will happen here? The load is not getting disturbed. There is a smooth flow of load from the system. Therefore, brick arch is good in compression. And then brick is also good in compression. You both play together, there will be no cracks in the arches. Nowadays, you can see most of the lintels, whatever we provide the first case, there will be a lot of cracks at the junction of the lintel and the wall because due to the disturbance of the load. Again, catenary curve. Again, you can see. Again, you can see the first case at top. I'm having a lintel, a bricks tied by a small thread rod. Instead, then what will happen? It will bend like this. There will be a tension at the bottom. Instead, what you do is you make it as a pre-compression. You provide a arch where the arch is good in compression and brick is also good in compression. Both will act together as a monolithic structure. So here, as provided by Rajendra sir, so this was the formwork, what has been placed over here for an arch. Then entire arch has been completed. There is no reinforcement at all. There is no reinforcement at all. Again, we have designed a staircase itself as an arch, okay, without any reinforcement. You can see, so elegant, I think so, from my point of view. So because again, here the mortar strength is more. It is 1:3 mortar strength. So he has done a lot of domes. So you can see there is no concrete at all coming up in the picture. You can see the entire structure. There is no concrete at all coming in the picture. Next about filler slab. So say for example, now I'm having a reinforcement. I'm drawing a reinforcement pattern. So this is reinforcement in a slab. Reinforcement in a slab. Now value stress diagram now. Value stress concentration for a reinforcement. This is stress concentration. Near the reinforcement, this will be these forces where you have maximum stresses. Okay, at this area, okay, this zone you will have maximum stress. Again, this zone also you will be having a maximum stress. What happened to this zone in between? There is no stress at all. There is no stress at all. So why do you want to put a large amount of concrete over there? Okay, instead we provide the bricks over there. Instead you provide some bricks over here. This is what normally I recommend, but many people they use instead of bricks, they go for a mangrove tile. They go for a mangrove tile. So it is up to the engineer what is his choice. Again. So here you can see we place a lot of bricks over here. In between we have reinforcements and then we provide even a electrical pipeline also in between. So only one thing is the concrete needs to be a good concrete and then the reinforcement, the slab thickness will be more than 150 mm or nearly to one, minimum is 150 mm because the thickness of brick itself will be 75 mm, 80 mm. And then concrete should not be dropped from height of more than 2 meters. That we should be dropped very gentle as they bring it down. So this is a reinforcement pattern. Okay. So this is how we have placed the reinforcements. So major advantage over here is since the brick is good in thermal insulation, when you provide for the roof slab, total heat generated outside, it will be only minimal coming inside. And here also, even for sunken also, they provided a bricks. But normally I don't recommend for a sunken to go for a filler slab. Instead for those sunken only you go for a normal RCC concrete due to the problem of water percolation. Here you can see how they place the reinforce, how they place the concrete, everything.
Hello.
Sir, hello?
Yes, sir.
Yes, yes.
You can see how the system is going on. Entirely it is.
No, sir, actually, we are not unable to see, sir.
We are unable to see the screen, sir. Actually.
Yes, sir. Oh, one second. No?
Yeah, okay.
But I can't see the screen.
Old.
One second. I'll stop and come back. Can you see now, sir? So can you see now?
Not yet, sir. Not yet.
Not yet. Now?
Yeah.
I can see something Microsoft Office that
Okay, one second.
box.
I don't know. One second.
Oh,
Now, sir? No. Now can you see, sir?
no, actually, the file is not accessing it. I can see some slides showing pillar plan.
Now is it clear, sir?
No, still we are able to see the folder only, sir.
Oh, okay. Shall I log in, sir? One second.
Yeah.
One second, now just.
Better, sir.
Okay. So can you make me co-host or no?
You're audible, sir.
Can you make me co-host to share?
Just give me a second, sir. Sir, proceed, sir.
Yes, sir.
Hello.
Yes, sir. Coming here.
Yeah, yeah.
Let us see now, sir, whether it is coming up. No clear, sir, video? Again, there's a problem. Am I right, sir?
I think the video format might be the problem, sir.
Okay, I'll send the video once again, sir. Okay, maybe I'll send you by Google Drive. You can share it. Actually, major aim
I
of
can
this.
share this.
Yes, sir. So now what will happen after concreting? The entire bottom surface, it will be like a, you can see the bricks projected outside. You can just do a simple plastering. The major advantage of using this rat trap bond and filler slab together is you can have a normal room temperature of 27 plus or minus 2 degrees centigrade. Even you get a winter season or maybe summer season. But to maintain this temperature only, we normally use air conditioning. Okay, so here what happens? The total cost of the building, as we done some 3 or 4 buildings in Chennai, the total cost of construction came down by 24%, exactly 24% when compared to normal conventional construction. And then they have not used any air conditioners in their homes. So therefore, what will happen? There is a less reduction in the electricity bill also. So that is a major advantage of going for rat trap bond and filler slab. Some cases, what I recommend is if you can't go for a rat trap bond, you can go for filler slab. This we call this as a locally we call the Madras terrace roof. Most of you will see across India before 1980s, 70s and all, they used to have only Madras terrace roof. The same concept Madras terrace roof has been developed into a filler slab. This technology has been approved by CPWD as well as Tamil Nadu Public Use Department and most of the government organizations. So people are not having that much awareness of this technology. They think that the building will not be safe. Someone easily poke inside the building. They may easily destroy break open the walls when it's going to rat trap bond. It's not so, because in case of rat trap bond, we go for a 1 in 3 brick mortar when compared to the normal conventional construction. These are all some of the constructions just been done by Sakti Rajendran sir in Tanjore. You can see that it has not been plastered at all. Okay, this has been surveying for past 30 years, nearly 3 decades. This is again building from other side of view, where you can go for elegant designs using a bricks, or elegant simple designs using a brick pattern. This is again they have gone for they are not providing any lintel over here. Instead, they gone for arches, where the compressive force has been transferred to the lower level without the disturbance in the load flows. Again, this target already we seen earlier. The same after finished surface, how it looks like. Again, this is a building, it's a structure which has come up in Periyar Manimai College in Tanjore, which has been designed by Rajendra sir. So they are not used even a single kg of steel in this structure. Okay, so entirely it was an arch or a dome. Therefore, it is done taken care of bricks. Okay, the brick wall was little larger in length. They have gone for a buttress. Again, the plinth was also designed using a brick plinth beam and from the open foundation. Therefore, they are not used even a single kg of steel. Again, see, already these have a good thermal comfort. To make it more thermal comfort, they are using the broken tiles on top of the arch. You can see the broken tiles. So therefore, the thermal comfort will be more higher inside the structure. So these are some of my acknowledgements. So I took most of some I had done from my own experience. Some I took from the earthquake tips for CVR Murthy sir and earthquake Bira buildings from subject to Gujarat State Disaster Management Unity Authority in Government and NP and most of the things I learned from my Professor A.R. Santakumar Lashimbadi, Head Professor Lashimbadi, who is a former from SRM University, and Engineer Rajendra sir, from whom I learned the cost-saving technologies. So these are my acknowledgements for presentation. So earthquakes do not kill people, only improper structures used to design do so. Thank you. Any questions? I'll be highly grateful. I'll give the question. I think so. I stick on to the time. Sorry, I could not share the last video, but anyhow, I share it to Girish Kumar sir either by WhatsApp or use a Google Drive. Thank you, Girish Kumar sir.
Okay, I'll share this. Yeah, very nice session, sir. Yes, Pujita, go ahead. Thank you very much, sir. We will wait for a while for some questions.
Okay, sir. I think so.
Are you able to see the chat box, sir? There are a couple of questions in the chat box. You can see.
Yes, sir. Coming up, sir. What is the cost of lead rubber base association system? I think so. In 2004, when they constructed it, was approximately 5 lakh rupees per lead rubber. So it depends. It depends upon the size of lead rubber. And now, with the recent presentation, I came to know from L&T, they reduced the cost of this lead rubber from 2.5 to 3 lakh rupees. And then after a lot of researches has been done. So in 2003-4 and all, many few people were using this lead rubber. Many people have started using many important structures like lifeless structures such as hospitals. They started using the lead rubber. Most of the AIMS hospital they are using the only lead rubber as a system. I think now the cost would have come down. It depends upon the size of the lead rubber, depending on the amount of stories, what load coming on lead rubber, it depends upon it. It will not be a standard value. Any other questions? I think so. People participate can also unmute. They can ask the questions also.
It is. Their hand. Yeah.
What are the future innovations in seismic design? It's a good question actually. Many people have started using the rotating towers. Okay, where the structure will rotate. The people think that when they start rotating, each and every you can see that you would have seen in the YouTube bundle rotating tall towers. Okay, but actually it will rotate exactly. It will take for one complete rotation. It takes 24 hours, similar to the rotation of the Earth. Therefore, if we see the sunset in the morning, Next day evening, you can see the again sunrise also, depending upon like that, the rotation has been there. Where you won't feel there's a rotation. Apart from that, nowadays we are going for blast resistant design. A blast resistance is not only due to the terrorist attack, it is even due to some blast loading. Say there is a sudden blast in a gas cylinder, suddenly the column would have collapsed. That's what the research is going on SRM. The sudden collapse in the structure. I think these are some of the future innovations is being designed. And then progressive collapse. Most of you would have seen progressive collapse. So progressive collapse means when suddenly one floor is going to collapse during construction or due to some other reason, the entire structure should not be collapsed. Something like a failure of a World Trade Center. Okay, but that is a different reason. It is called the continuous collapse of system. Can the increase of the structural elements dimension will suffice for earthquake disaster? Yes. When you increase the structural element, it will resist more earthquake load. And normally, for any structural design, whether it be steel or RCC, the major aim of a design is to first it should be safe. The second, it should be serviceable, and third is only economic. So safe means everyone thinks that I will get a very good design. But say for example, even a slab of 100 mm thick, okay, it may be safe in collapse, but it may not be serviceable. You may have a small cracks coming at the bottom of the slab. Even though you put a larger good reinforcement, there will be a small displacement you can feel when you go on top of the slab. Therefore, the structure should be safe, it should be serviceable, and then it should be economical. Put some light on how to assess the building before and after retrofitting performance assessment. Say for example, now we have designed one of my client, it's not my client, I say client's friend has done a structure. So the concrete grade, what they have provided was only M20 as per the design. But the column, what they have concreted was not a good concrete, 3 or 4 columns. When we gone for a core cutting, okay, when we have gone for a core cutting, so we say that grade of concrete is only 6.5 MPa. Normally, as per the design, it's going to be M20 grade concrete, I should get 20. If it's going to be a column, we take 0.4 FCK. Okay, so 0.4 FCK means 0.4 times of 20, it should be 8 MPa. But actually, the grade of concrete is only 6.5 MPa. So what we done was we are to increase the moment capacity as well as the axial load. But from 8 MPa, I can't take it to 20 MPa. That's impossible. Okay, so I want to make it safe for 8 MPa. Okay, so what we have done is we have done a carbon fiber reinforced plastic that we wrapped around the column. I don't know how to assess the structure, but we have assessed in our university by wrapping the RC column some 10 years back. So RC column wrapping, the load carrying capacity has increased. What we did is we took a small column of 200 by 200. We applied the load. We made it fail. Then again, we retook the same column. We wrapped it together. Okay, and then I by some paste and all. Again, we apply the load. We get the same load. That is how we can assess the retrofitting after the retrofitting. I think so. That is what my point of view. What kind of seismic resistant design is necessary for industrial structures where heavy loading complex geometry exists? Okay, whenever there's going to heavy loading, there's no other go. We have to make the structure to be robust. The only thing is we have to make the structure to be robust, and then we can provide shear walls. Okay, at the end, most extreme case, we can provide a bracing. So normally, people, they don't go for heavy loading for industrial structures. Normally, they don't go for G+1. So most of the industrial structures, they have a heavy loading only in the ground. They plan such a way that they have a only heavy loading only in the ground. They don't plan it at the upper level. If they want to plan the upper level, there's no other go. We have to go for robust structure by providing shear walls and structure. I think so. That will be the best idea of going the system.
Thank you, sir. Thank you for sharing valuable information with us. Hope your doubts were clarified. Feedback link is posted in the chat box. Kindly fill the feedback. Thank you all for participating.